Yeah. I'm still sore. Oh, I never really decided much.
Uh, I decided to move the test to not next week, but the week after. Yeah.
Yes.
Um,
Yeah.
so welcome back. So I decided that wait, so I guess the tests got even moved further. So this is this week. And then there's the homework 7 that's supposed to be due today, but it'll still be open a little bit longer. And then homework 8 will be the last homework that's going to be covered on test 2. So test 2 will have like I guess 4 homeworks on it. It's just the second order equations. I just want to make sure that test 2 just does all the well, the idea is that we're going to cover the rest of spring mass systems, and then we're going to start electrical circuits, and I want at least electrical circuits to be on this next test. So just because we're not going to get through electrical circuits until through this week, it would be a little bit aggressive to have the test like right after we've just covered that stuff. We may also have like second higher order equations, and maybe depends on how far we get. So whatever we end up finishing this week is the cutoff for the test on April the 1st. So it's like I pushed it because of that. But when we were here last time, we were talking about this a problem where you have a forcing on. So this idea that like you can have all these different forces. We talked about let's just go back and just look at it. We talked about how you could have F equals MA, and your MA can be your force in your F equals MA is just all the force that's acting on your object, which originally was just the spring force. Then we were like, let's add resistive forces like friction or air resistance. And then if you tilt it vertically, there would be like a constant gravitational force acting on it. And all of those are just going to become your big F. And then on top of that, we decided that we might even add an external force. Gravity is like an external force, but it's just like a constant external force. What if you have like active shaking? That's an external shaking force. Then that's a function that's not necessarily constant. It's a function that is dependent on time. And if I wanted to look at shaking, then the shaking could be described as this F of t, this external force is capital F times cosine of omega t. This is like saying I'm shaking at an amplitude of capital F at some circular frequency omega. And so that's happens in real life, various in scenarios that would describe some external forcing like that. So then I looked at, let's say friction is absent. So let's say friction is negligible. Then you can look at a situation where you have, some mass, no damping, so delta 0. And then I give you some information. So if it's a vertical spring mass, then you can always find what your spring constant K or stiffness constant K is. If I also give you that a certain mass was displaced by a certain length beyond its natural spring length, that's how engineers in practice compute the stiffness constant of a spring. And so we went and did that, and then we got this equation, no damping, so there's no delta, and then you can solve this because this is just a homogeneous equation. And so we have this homogeneous solution is some not unexpected, right? Because if you have no damping, then you're going to have just a simple harmonic motion oscillation, which is going to be these things, the C1 cosine of 3t, C2 sine of 3t. And the frequency of this harmonic simple harmonic oscillation is going to be 3. And I'm going to make a point here and say this is my omega naught. and there's a different omega up here. So omega naught, I'm going to reserve to be the natural frequency of the spring mass system when there's no external force. So that's like your homogeneous solution. And then the external force I decided to put on this is like we're shaking this at a rate of a certain rate that's described by this cosine of 3t with an amplitude of 2. And this external shaking is also got the same circular frequency as your homogeneous solution. This is like this is simple harmonic motion. So this is like no damping, let it just be just vibrating up and down. There's no resistance, so no damping means that it'll just do this forever. But then I'm also going to shake this, and I'm shaking it at the same circular frequency as the actual object is already shaking on its own. When you're trying to solve this, using method of undetermined coefficients, you always build your particular solution based on your right-hand side, and you'll notice that it's exactly the same as your homogeneous, so there's no hope of this solving the original differential equation here. It's going to solve the homogeneous equation instead, so we have to multiply by t. And then you end up doing a lot of product rules, and then you solve for your A naughts and your capital A and capital B, and then you'll get your particular solution. You add the homogeneous solution with it, and then in this one, it says that you're displacing it 1 centimeter downwards from the equilibrium position. So the equilibrium position has already been stretched due to gravity, and that's the coordinate system we're using because we said that that way you can say the homogeneous solution already includes gravity. And then the initial velocity is 0. That means that you're just stretching it downwards from the equilibrium position and then letting it go. Those two conditions, if you plug into your general solution, will give you your C1 and C2. And then this is the final answer. And so this right here is your solution that is going to be how the position of your mass is changing due to the fact that you pulled it down and you let it go. If you pulled it down, this it's like this this vertical spring mass system. If you pulled it down beyond the rest position being the equilibrium position, then it's been stretched, so the spring is going to want to pull it back up. But on top of that, you're shaking it up and down at the same frequency that it naturally vibrates. And so that's causing your motion to actually blow up. So this red right here is the red part. So this cosine of 3t, that's just your homogeneous solution, is your red part. This is like the position as a function of time if you didn't have any external forces. It's the simple harmonic motion, no resistive forces, but also no external forces. This is how it will vibrate forever if you just let it go. Now, if you add a shaking to it, that actually is the same frequency as the natural vibrations of your object, then you have this green. So this green one is just whole underlying thing, which includes this purple term plus this red term. And it's the purple term that's actually causing the amplitude to blow up because I made an arrow here. It says that there's a t here that got multiplied. And so that means the amplitude for your purple term grows as time goes on, right? Because this t is going to grow. This one's going to have a constant amplitude of 1 the whole time, right? And so the combination of those two give you this green. If you don't have the purple and just the red, then it'll just be this. And the reason there's a t there is because we had to multiply it by t right here. And that was because the particular and homogeneous solutions, they look the same. And so you had to multiply by t. And that t, why did these look the same? These look the same because they had cosine of 3t, and sine of 3t, and sine of 3t. Basically, you have a homogeneous, so if you have no damping, you're going to have a trigonometric solution like this because you'll have complex roots for your characteristic equation. Your right-hand side being a trigonometric function will also make your particular solution be a trigonometric form like this. And then the only way you're going to get these to match is if you have the same argument. So this is a cosine of 3t, this is a cosine of 3t, and a sine of 3t. And why would you have the same argument is because the omega naught, which is the frequency of your harmonic oscillation, your natural oscillation of your system, matches the same as your external oscillations. So basically, if you have your omega naught being your natural frequency of your system is the same as your external frequency, so you're shaking it at the same frequency as it naturally wants to vibrate, that's going to cause something called resonance, which means that it's going to amplify the vibration so that it grows like this. And people have different additional names for this. So this red term is your homogeneous solution, XH, but people call that also the free response. It's the response of the system if you just let it be on its own, like it's free. And then the XP is your forced response. It's the response that you are causing the system to have due to your forcing, which is the shaking that you did. So that's called the forced response. And so if you have a spring mass system with no damping or very, very small damping, in practice, you may not be able to completely eliminate damping, but if it's very small, negligible damping, then your second order differential equation will not have an x prime term because your delta x prime term would be 0. And then let's say you have an external sinusoidal force of this form. Resonance will occur whenever your natural frequency, circular frequency, omega naught, equals your so I'll just say this is your natural frequency of your system, which is your omega naught, equals your circular frequency, forcing circular frequency, which is caused by your if these two are equal to each other, then you'll have resonance occur. So this will cause resonance, like this condition that they're both equal to each other. And we also know that omega naught in the case where you have no damping. So this is for no damping. If you have no damping, we did talk, we did this in the past, that this would mean that your omega naught would be square root of k over m. You can confirm that just by solving the characteristic equation for general m and k when there is no damping. This will be, it's not going to be this if you have non-zero damping, but whenever damping is 0, omega naught, which is the homogeneous frequency, will equal this. And so if if both your frequencies are the same, external and your natural frequency are the same, then you'll have the same, you'll have resonance occur. And so I guess I should make a note here that your forcing frequency is technically omega naught over 2 pi. So there's a difference between circular frequency and your so remember, omega is your circular frequency and it's equal to 2 pi f. F is your actual frequency. So just want to make that note here. So if you see like somebody asking you to compute the frequency that would result in resonance, they're probably asking you for the actual not the circular frequency, but the frequency where you're dividing the circular frequency by 2 pi. And of course, if these two will only equal to each other, if and only if omega is equal to omega naught. Or I'll just do omega equals to omega naught. And so this is like a cartoon that shows you what happens if, let's say, the wine glass has a natural vibrating frequency, and then you actually, this person singing at the same frequency that the wine glass naturally vibrates at, then it will cause resonance, which means it'll vibrate with a higher and higher amplitude, and then usually that leads to some kind of failure in the system, which means in this case it breaks. So let's look at the same problem, previous problem, but now we have a periodic external force of 2 cosine of t. So we're going to go back and just say, okay, we're going to have the same problem as this. So all I'm going to do is I'm just going to take this right here. But the difference is now I'm going to take this and then take the frequency, the external force to be equal to this 2 cosine of t. So instead, I'm going to use this right here. So this is what different from before, but everything else is still the same in terms of like the so the homogeneous solution will still be this, right? So because it's the same equation, only thing I changed was this right-hand side, but the homogeneous solution would still be is just the same equation with the 0 on the right-hand side. So this is still the same. Now I'll propose a particular solution. The particular solution will be equal to, you're building it off of the right-hand side. So in this case, your particular solution would be a cosine of just t plus b sine of just t. Not 3t, because all I did was I took the cosine of t, 3t, and then just got rid of the 3. So we just have this, but there is no matching now. Everything is fine. These two don't have any terms that match, so we don't have to multiply by t. So we're going to see that this is an easier problem because of that, because you just take the derivative. It's going to be negative a sine of t plus b cosine of t. And then xp double prime is going to equal negative a cosine of t minus b sine of t. And that's only so that you can actually, plug it in to the differential equation and solve. Let's just do that. So you'll get like, you're plugging in the negative a cosine of t minus b sine of t. That's the x double prime term plus 9 times the original xp, which is the cosine of t plus b sine of t. And then this is going to equal your right-hand side is 2 cosine of t. And then you're just going to match terms. So I'll just say that I want my cosine terms. So there's this one right here and this one right here has to match with that. And then all my sine terms, which are this and this, has to vanish. So basically, I can just look at these two together. It's going to say that negative a, I'm going to distribute the 9 on this, plus 9a has to equal 2. Okay, that's the cosine terms matching. Then we need to look at the sine terms. The sine terms are saying it's just a combination of these two now. So it's going to be negative b, and then the plus 9b has to equal 0. This one's going to be very simple because it's just saying that 8b has to equal 0, so therefore b has to equal 0. So that's that one. This one's also not that hard. So you're just going to say that you're going to have 8a has to equal 2, so therefore a has to equal 1 over 4. And because the b is 0, your particular solution, okay, we'll just go up here now. Say your x of t is going to be this form, but with b is 0, that means that a is equal to 1/4, so it'd be 1/4 cosine of t plus the homogeneous solution, which is this stuff. Just move this over. Okay, so that's the general solution. And we're gonna, so this is still your general solution, so I'll just say general solution. We want to find the actual solution that solves the initial value problem. And the way you're going to do that is apply initial conditions. So what does it say? Displaced by 1 centimeter downwards from the equilibrium position. And then it's just simply let go so that it has an initial velocity of 0. So it's a vertical spring mass system. The displaced by 1 centimeter downwards means that x of 0 is equal to positive or negative 1. We use the convention that stretching is positive. So down was actually positive. So this will be 1. And then your initial velocity is just 0. So I'll just say x prime 0 equal to 0. So those are your two conditions. You're going to have to take the derivative of this, which is x prime. I'm going to shift all this over. So you'll have x prime is equal to, you take the derivative, negative 1 over 4 sine of t. And then you'll have minus 3c1 sine of 3t. That's just the chain rule. Plus 3c2 cosine of 3t. You need the derivative eventually, but the first condition I'm going to use is the x of 0 is equal to 1. That one is going to give us that you have 1 is equal to 0 plugged into all of this would just give you 1/4 plus c1, because this is sine of 0, which gives you that c1 is equal to 3 over 4. And then you need to plug in your other condition, which is x prime of 0 is equal to 0. That's going to mean that 0 is equal to, plugging in 0 into all your x primes, would be 3c2. Of course, that just means that c2 is equal to 0. So we've got our two C1s and C2. So that means in this general solution here, this C1 is equal to 3 over 4. And then this C2 is equal to 0. So with that, your eventual answer to this is going to equal x of t is equal to the 1/4 cosine of t, which is your particular solution. So I'll use purple. Plus your homogeneous solution after applying the initial condition is just this term right here, because the other term had C2 was 0. So it'll just be this. 3t. So your forced response is the purple one, and your free response is the red one. And I'll use blue, because I want to make it clear that this is actually the blue graph right here. And the red graph is just the free response. So the free response being just the part when you let it be on its free on its own, like how it's going to vibrate free on its own. And then if you do the whole thing, which is the free response plus your forced response, basically your homogeneous and your particular. The particular only comes from the fact that you've been shaking it externally. If you include both of those, then instead of the nice, pattern of the red just keeps going the same way. The blue has some little changes going on because that's due to the effect of the external shaking. So red is like if you don't do any external shaking, this is how it will vibrate on its own forever because we don't have any resistance. We're assuming that the friction is 0. So it'll do that forever. But if you actually shake it by this thing, but this thing right here isn't shaking at the same frequency as your natural frequency of your object. It's going to have some effect, but it's not going to cause resonance. And this is what typically happens. It won't blow up, it only blows up whenever you have it vibrating at the same frequency as its natural frequency. So it is just doing something like a little bit weird where the blue is just shaking a little. So the blue is what it's actually going to look, how it's actually going to shake if you have this external force as well. No resonance because the frequencies are not the same. And basically it shows up as no resonance in the sense that your particular solution form that you come up with first doesn't have any terms that match with your homogeneous, so you don't have to multiply by t, and that multiplying by t was the reason that you had a forced response term with a t, which means an oscillation that increases in amplitude as time goes to infinity. So this is what you'll have if you don't have resonance, something like that. So we could like play around with this and see what kinds of behavior you might expect to see based on different kinds of forcing. And so let's see if I can open this. Okay, so let's look at if you have, let's turn off, so let's say you have this, we're doing the same example we just did. The example we just did had a free response, a homogeneous solution. This is like how your system would respond with no external force. That's 0 on the right-hand side, and no resistance. The reason why I don't want resistance is because if you have resistance, then the natural frequency of your object will just decay with time and it'll just disappear. And I just want to see like what hypothetically, if there was no resistance, then it can vibrate on its own forever like this, and then you also introduce an external vibration to the system, what would happen? So the purple thing is my external vibration, how I'm going to shake this thing. It's my capital F cosine of omega x, okay? And I have control in tuning your external force, your external shaking. I can change its amplitude F, right? That's how strong I'm shaking it. Of course, if it's 0, then it's like no external force. And then I can also tune the frequency, which is like taking this W and increasing or decreasing it. That's changing the circular frequency of your external vibration. And so what is going to be the omega that will cause resonance? Yeah. So if I raised it to something close to 3, like, I don't know, like that, and then I'll turn on the, this is like just the solution. So I'll turn that on. So if you see, that's resonance right there. Okay, so what happens if I decrease the amplitude of my external force to 0, what do you think the blue line is going to turn into? It's to the red line. Okay. The purple dashed line is 0 because we just caused the external forcing to just go away. And so now your object is just going to vibrate as it would normally vibrate. Now, if you increase the forcing frequency, not the frequency, just the amplitude of your forcing, then it's going to resonate. In this case, because your circular frequency, external frequency is 3.02, which is like close to 3, right? If it's exactly 3, then it's going to be even better, but it's enough to be close to it, right? You already see the blue one is blowing up. Now, if you change this external frequency, and it's going to blow up more and more as you increase what is this doing? This bar is just saying I'm shaking. This is fixed, so it's like I'm shaking at this frequency, which happens to be very close to the natural frequency of our system already. And now I'm just shaking it even harder and harder and harder. So that's why the blue is blowing up more and more and more if we increase that. Now let's fix the forcing, the amplitude of the external forcing, and then change the frequency. As I move this to the right, what do you think the blue is going to end up doing? The blue being the motion of the actual motion of the object. Now we're going to keep the external forcing amplitude the same, 4.5, but I'm going to change the frequency, make it higher. Do you think you're going to see these, this blue that's blowing up, will it blow up more or less, or what? It's going to go down, right? Because it's going to break resonance at that point because you're not going to be oscillating at the same time. So I'll move this to the right. And so it breaks the resonance. And so it's going to just not resonate anymore. Now let's go back. Of course, we could go backwards. And then as you approach 3, it's going to gain resonance. It's going to return back to resonance again. But then if I keep moving to the left, what do you think will happen? It will also, the resonance would disappear. Okay, so let's look at like, like right here. Why am I looking at this one? Is because just by looking at it, I just wanted to look at this time right here. There's a kind of an destructive interference going on at this moment right here, where the shaking is telling me to the shaking is pushing the object in the upward direction like this, while the natural frequency of your mass is saying I want to go down, right? So the blue is just a compromise of those two. So the blue is just going to be where it's going to go based on how I'm shaking it and how the object wants to vibrate. Now, in this case, my purple is quite big, right? The amplitude of my external shaking is quite big. So that's why the actual motion of the object is actually upwards towards the purple. If I make this F, which is the external frequency, go down, what do you think the blue is going to do? This hump right here, just this hump right here. It'll go down, right? Because the influence from my external force is going to be decreased. And of course, we know what's going to happen in the limit, that we don't have any external forces anymore. It'll just be back down. Now, if I say I'm going to vibrate this external force, so we're just looking at this spot right here, we're going to have a little bit of a bump here. The more we have the external force stronger and stronger, it's going to compete against the natural vibration of your thing, but then it's going to win out if it's big enough at that point, right? And of course, you could also like tune this where it's like, I don't know, like right here. And let's do this. So that's just how the external force is affecting the natural vibration of the thing. What else can I look at? So this one is like saying I'm gonna vibrate very slowly. So like the object is vibrating at this red frequency, but let's say I'm shaking it very slowly. That's like the purple right now, So what's happening is if you look at the blue, it looks like there's like two sort of scales to it. There's like I don't know if the right word would be like, there's like a large macro vibration, where it's like this like blue is like shaking kind of at like the same shape as this purple. But as it's doing that, it's vibrating with these micro vibrations that are kind of at the frequency of the red, So if you look at this, there's like a trend where it's like, if you just ignore the fact that it's wiggling, very, very small wiggles, the large wiggling of the blue is kind of represented by the purple dashed frequency. But as it's doing now those large vibrations, it's like it's doing this, but within that, it's vibrating very, very small. And that small vibration is mimicking what the red motion is doing. So it's like it has a natural frequency that I like to vibrate at, but this guy is also causing me to vibrate in these long wavelengths. And so that's why it's like I'm gonna shake very, very small while also shaking in this longer. So there's like multiple scales there. I think that's enough to explore. Of course, you can animate this where it's like just moving these on its own, but you can see how the interplay between, so the red is not changing because that's the natural. The only thing I'm changing is the purple, both the amplitude and the frequency, and you're going to see resonance breaking, and how the external force influences the motion of your the mass. Okay, that's fine. Does anybody have any questions about it? Okay. So back to this. When I post the lecture notes, I'll put a link somewhere here so you can actually open this on Desmos and you can play with it if you want to. So that's without friction, but what if we do it? What if we introduce friction? Then you're gonna obviously have some other, so this is like going to introduce a delta term if you introduce friction. So let's just start with our equation. When you have damping, it's going to be mx double prime plus delta x prime plus kx. And then we're going to have some external force, which they tell us what it is. So it's this right here. So let's say you have a force of 5 cosine of t. They give us all the other information. So for our problem here, our mass is 1. So that means you just have x double prime plus your spring constant and damping coefficient. So damping is 3 x prime, and your spring constant is 2. And this is going to equal your 5 cosine of t. I'll make that purple. So I'll just say that that's my external force. And you can solve this, right? This is just a review, I guess. The only thing that's new is trying to take all this and put it into the right places in your equation. But, if you want to find the homogeneous solution, you just do the characteristic equation. And this factors to r minus 1, r plus 1, and r plus 2 is equal to 0, which means that r is equal to -1 and -2. Okay, question, is this overdamped, underdamped, or critically damped? It's overdamped. How do we know it's overdamped? We know it's overdamped because you had two real solutions to your characteristic equation. If you had two complex, then what would be the underdamped, critically damped? Underdamped. And if they're repeated, then it's critically damped, right? Or you can use that discriminant of the quadratic form. That's, the d squared minus 4ac is greater than or equal to or less than equal to 0, that kind of condition. But it's also consistent with this. So that means that we have a system here that's overdamped. So that means that if we let it, unlike the previous ones where we had no damping, so we had simple harmonic oscillation that kept on going forever. In this case, we have damping and quite a bit of damping because it's over damped. So if you just let it go on its own, it won't vibrate. It'll just return back to equilibrium and just stop because of the damping. And then but what you're doing is you're still shaking this thing. So the particular solution is going to be trying to find the forced response of the system, the response of the system due to the external force. And because your right-hand side is this, you're going to say a cosine of t plus b sine of t. And you're going to find, xp prime, which is going to be negative a sine of t plus b cosine of t. And then xp double prime is going to be equal to negative a cosine of t minus b sine of t. And then you're just going to plug this in. So when you plug it in, you're going to get negative. It's just going to be this. So I'll just say this guy. And then, nope, just one of them is enough. What is it? 3x prime. So I'll just do plus 3 times the x prime is going to be this one. And then you're going to add to this plus, I forgot to put an x right here, sorry. this is like x double prime x, and then it's k times x, 2 times x. So it'll be 2 times the a cosine of t plus b sine of t. And this has to all equal 5 cosine of t. And you're just going to multiply things out. So it's going to be, I'm going to look at, we'll just say that you have this right here and this right here. So I'll just look at these two right here. That combines to, well, we could just do everything at once. So you'll have negative a cosine of t. But then there's a 2a cosine of t here. So that's going to combine to give you just 1a cosine of t. And then there's a plus 3b cosine of t. I'm just writing all the cosine terms. And then the sign is minus and then a plus. So it's going to be 1 plus of that. And then a minus 3a sine of t. And this is 5 cosine of t. And then you're just going to match things. So you're just going to say that I need my cosine terms to all add up to this right here. And then I need my sine terms to all go away. So the conditions that we're going to have is that b minus 3a has to equal 0. And then we need to have a plus 3b has to equal 5. So this will give us that b has to equal 3a. And then I'm going to just plug that into this one. So this is, with that, this is going to be a plus 3 times 3 is 9. A is equal to 5. And so you're just going to have 10. You have 10, and so a is going to equal 1/2. And then that'll give us that this has to equal 3/2. So this is my b, and this is my a. And so our solution is going to be eventually taking the general solution is going to be the particular solution plus the homogeneous. So in this case, your particular solution will be half of cosine of t plus the 3/2 sine of t plus the homogeneous solution. The homogeneous solution is this thing right here. And let's just take this, say this is what it is. Does it give you initial conditions? It doesn't give you any initial conditions. So this is your general solution. And I guess we don't have, okay, maybe there's a little bit of time so I can talk about how, let's just do the, well, let's just well, let me make this comment first before I tried. I was going to say that maybe it'd be good practice to write the particular solution in amplitude phase form, but we don't have to do that necessarily. That would have been nice if I had time, but I'm just going to move this down and just make a comment with regarding this last slide right here. So what do you observe? Let's look at what happens to this term right here, your homogeneous term. Let's say, what is this going to approach? as you make t go to infinity. This blue term. No matter what your C1 and C2 is. So we didn't compute what C1 and C2 are, but they'd be some numbers. But if you take t goes to infinity, both of these terms would go to 0. So this is what happens because of damping. Damping is going to make this free response, which means like the system without any external force, just letting it be on its own. Because of damping, it will go away. Why did it not go away previously is because we didn't have damping. So your homogeneous solution, if you have damping, will always decay. Now, it could be, this is over damped, so it's going to decay pretty fast. Critically damp will also decay. There's going to be like a T times E then something, but it's always going to be E to the some negatives, something times negative T. So the T will grow, but the exponential grows faster. And so the E to the negative. So critically damped is going to be like something like this will be critically damped. As you as you make t go to infinity, what is this going to be? It'll still be 0. You could do L'Hopital's rule on this, right? Because the e to the negative t will decay much faster than t growing. T will definitely grow as you make t go to infinity, but this e to the negative t will dominate it and make it go to lower. So critically damped will also disappear. And then under damped is going to have something like this times, some C1 cosine of t plus C2 sine of t or something like that. But this will also go to 0 as t goes to infinity because this exponential term will decay. So any homogeneous solution, overdamped, critically damped, or underdamped, as you go further in time will disappear. That's the whole point of it being damped, is that it damps away. So you will be only left with your forced response. So this is why it's saying your free response is transient. So if damping is present, so delta is greater than 0, the free response, which is your X homogeneous, is always transient. Transient mean that it will disappear over time. This just is saying that the limit as t goes to infinity of your homogeneous solution, so long as damping is present, whether it's overdamped, critically damped, or underdamped, will always go to 0, which means that with time, you will only have the forced response, which is the particular. This one won't decay. This half cosine of t plus 3 over 2 sine of t, if you increase t, will not disappear. It'll just stay. And so that's why if you're looking for the long-term behavior of a system that's damped, it'll just be the particular solution over time. All your other, your free response, whether it's critically or overdamped, you can see from these graphs that they get damped away. So that concludes this where it's perfect because then we can pretty much start with electronic circuits on Wednesday. There might be a little bit I might want to say about like writing this in amplitude phase, or I might just post it and you can look at it. But that was just extra. We don't have to do that because we already talked about amplitude phase. But we'll try to move and do the electronic circuits next time. Have a good day.